All right, greetings YouTube, beautiful mind here. Let's see. So this will serve as the lecture for week 5 Wednesday for Calculus 1. I hope everyone is doing well. Exam 2 was due this past Saturday at 11:59. I think Moodle is updated, is up to date. Let's see. There is what is it? There is a assessment that is available on Pearson. I mean on Moodle. You want to definitely go ahead and do that. You get one attempt at it. Yeah, and it'll count as a quiz grade. It'll have a low weight, but it will be part of the grade. Right. So there's an assessment that's available on Moodle. Just take it at your convenience. You get one attempt at it. So take it when you feel like you're ready. It's just kind of general topics. This week, just kind of be sure to get our assignments submitted properly and be on the lookout for a quiz. It might already be loaded. So my intent is when I'm done with the lecture for today to go ahead and update all of my Pearson stuff, make sure everything is loaded for the week, quizzes and things of that nature. So if you see it, remember with all of our assignments, they're available pretty much the whole time. We get a limited attempts at them. I think this class is good. I think everybody here has full access to Pearson. Yeah, and just know that I'm available for questions. So, I mean, you guys seem like you guys are making your way through the material. I think you're starting to see the power of Pearson. Like, you're making use of your resources. So, however you're doing it, whatever you're doing, it seems like it's working. So we're going to go with it. Let's see. So for today, we're going to move into chapter 4, applications of derivative. And we want to talk about the maxima and minimum. Let me see. Imagine taking a long hike through varying terrain from west to east. Our elevation changes as we walk over hills and through valleys and across plains. And we reach several high and low points along the journey. Analogously, when we examine a function f over an interval on the x-axis, its values increase and decrease, reaching high points and low points. We can view our study of functions in this chapter as an exploratory hike along the x-axis. So we're going to let f be defined on a set D containing C. If f of c is greater than f of x for every x in the domain, then f of c is called the absolute maxima. And analogously for absolute minimum. So basically, an absolute maxima is, like, in a graphical sense, is just going to be the peak of a mountain. And the absolute minimum is going to be the bottom of a valley. Okay. We say an absolute extrema value is either an absolute max or an absolute min. Okay, let's keep going. Let's see if we can see this. So the existence and location of absolute extrema values depend on both the function and the interval of interest. Okay, so like for instance, if we look at this part A, we have an absolute max when x is 0, an absolute maximum value of 4 when x is 0, right? But then for part B, we still have an absolute max of 4 when x is 0, and now we have an absolute minimum because our range is restricted from 0 to 2. In part A, we were considering the whole domain, so there was no minimum value, but there was an absolute maximum value. For part C, notice that we're doing the half interval, where the open interval we don't include 0, but the closed endpoint of 2. So there is no absolute maximum value, but there is an absolute min. And then in part D, we're doing the complete open interval from 0 to 2. There is no absolute max and no minimum. Okay. So defining a function on a closed interval is not enough to guarantee the existence of an absolute extrema values. Okay. So we have to kind of be on the lookout if we have discontinuity as well. Let me see. So it turns out that two conditions ensure the existence of absolute maximum and minimum values on an interval. The function must be continuous on the interval, and the interval must be closed and bounded. So a function that is continuous on a closed interval AB has an absolute maximum value and an absolute minimum value on that interval. So if the function is continuous and is closed and bounded, closed meaning we include all points, or all points are included, like there are no open intervals, right? Let me see. So we have this example 1. Locating the absolute max and minimum values. For the function in figure 4.4, identify the location. Identify the location of the absolute maximum value and absolute minimum value on the closed interval AB. do the functions meet the conditions of the extreme value theorem? So let me see. So in both cases, we're considering the closed interval a, b. Notice that function a is continuous. So the absolute max is going to occur on the far left, and absolute when x is a, and the absolute minimum is going to occur when x is c. But notice that for part B, it's not continuous, right? We have holes, gaps, it's the open interval. All right, so there is an absolute max, but there's not an absolute minimum. Let's see, how do we do? So for A, the function is continuous on the closed interval, so the extreme value theorem guarantees an absolute max and absolute minimum. So the max occurs when x is a, and the minimum occurs when x is c. The function g does not satisfy the conditions of the extreme value theorem because it is not continuous, and it is defined only on the open interval ab. It does not have an absolute minimum, but it does have an absolute max when x is c. Therefore, a function may violate the conditions of the extreme value theorem and still have an absolute max or min, or both. Okay. So then we want to introduce this notion of what do we mean by a local maxima and minimum. Figure 4.5 shows a function f defined on the closed interval ab. It has an absolute minimum at the endpoint b, to the far right, you see it there, and absolute maximum, probably at s, at the interior point s. In addition, the function has a special behavior at q. Notice at q we have a sharp corner or sharp turn, where the value is greatest among the values at nearby points at p and r, whereas value is least among values at nearby points. At a point at which a function takes on the maximum or minimum values among values at nearby points is important. Okay. So we have this notion of what do we mean by local maximum and minimum value. Suppose c is an interior point of some interval I on which a function is defined. If f of c is greater than or equal to all f of x for all x in the interval, then f of c is what we consider to be a local maximum. And analogously, if f of c is less than all f of x for all x in the interval, then f of c is considered to be a local minimum. Okay. In this text, we adopt the convention that local maximum values and local minimum values occur only at interior points of the interval or intervals of interest. For example, figure 4.5, the minimum value that occurs at the endpoint B is not a local minimum. However, it is an absolute minimum. So, okay, so for this context, whenever we see local max or min, we're talking about interior points. Apparently we're not going to use the endpoints as absolute max, as local max or min. The endpoints have the potential to be absolute max or absolute min. So let's look at this example too. Locating various maxima and minimum. Figure 4.6 shows the graph of a function defined on the closed interval ab. Identify the locations of the various maxima and minima using the terms absolute and local. Okay, so we have this over here. Let's see. It looks like we have an absolute minimum when x at x equal to p. Is one higher? It seems like the max. Okay, so apparently we can't have the absolute max. Yeah, it can occur. It could be an interior point. So the absolute max is going to occur at q and s. So it looks like we have two. Well, we have one value, but it occurs twice. Sorry. Yeah, absolute max. And then local, we have a local min at p, and at r we have a local max at q and s. So the local max, let's see, how do we do? So we have it here. So the function is continuous on the closed interval. It has an absolute max and min on AB. The function has a local minimum value and its absolute minimum value at P. So local min and the absolute min at P. That's fine. It has another local minimum value at R. Oh, yeah, that's another local minimum. It's not the absolute min, but it's a local min at R. I forgot about that one. The absolute max occurs both at Q and S, which corresponds to the local maximum values. Okay. So then critical point. So another look at figure 4.6 shows that the local max and min occur at points on the open interval AB where the derivative is 0. Again, the slope of the tangent line is a horizontal line, or it's flat. or 0. And at points where the derivative fails to exist, for instance, where x was p. We now make the observation precise. Figure 4.7 illustrates the function that is differentiable at c with a local maximum at c. For x near c, where x is less than c, blah, blah, blah. Long story short, if f has a local maximum in value at c, then f prime of c exists, and f prime of c is going to be 0. So if the function has a local maximum in at c, and the derivative exists, then we're going to say the f prime of c is going to be equal to 0. So the slope of the tangent line at that local max or min, if it exists, if the derivative exists, is going to be 0. So local extrema can also occur at points where at point C where f prime of c does not exist. Figure 4.8 shows two such cases, one in which c is a point of discontinuity and one in which f has a corner point. Because local extrema may occur at points where the derivative is where f prime is 0 or where f prime does not exist, we make the following definition. So a critical point, an interior point C of the domain of f at which the derivative is 0 or the derivative fails to exist is called a critical point of f. Right? So we have like a function. Note that the converse of theorem is not necessarily true. We a local minimum at C where f prime of c does not exist. Right? A local maximum at c where f prime of c does not exist. So those are two examples where the derivative does not exist, but we have a local extrema. Okay. And then note here that even though the derivative is 0, that doesn't guarantee that it's a local max or min. Okay. So finding critical points. Note that f is find the critical points of f of x equals x squared times the natural log of x. Okay. So to find the critical points, those are going to be where the derivative is either 0 or does not exist. Okay. Let's see. Paper. Let's go like this. So if we have f of x equals x squared times the natural log of x, right? So you see the graph over there. If we have x squared equals natural log of x, let's observe f prime of x. So we have to use the product rule, which is going to be the first times the derivative of the second plus the second times the derivative d by dx of the first, right? So then this is going to be, what is that, 1 over x? So that's going to be x squared over x plus 2x times the natural log of x. So then this becomes x plus 2x natural log of x. Okay, let's see if we can find our critical points where this is either 0 or does not exist. I don't think I need that much more paper. Let me see. So if we set this to 0, let me see, we could factor out an x from both sides. So we can have x times 1 plus 2 natural log of x equal to 0. So then from here we get that what? X equals 0, or let's see, if we have 1 plus 2 natural log of x equal to 0, if we solve that, if we subtract 2 log x equals negative 1, we can't take the log of a negative, right? Let's just keep going. Let's keep going. Okay. So then we have the natural log of x equals a negative 1/2. So then to solve, we say both sides to the power of e. So then x is going to be e to the negative 1/2. might have to impose a restriction that x has to be non-negative, positive. Yeah, 0 is going to make it undefined, right? Log of 0, that's going to be undefined. Okay, so the critical points I get are x equals 0 or x equals e to the negative 1/2. Those are the critical points that I would check. Let me see. I kind of want to shrink this down. Okay. Let's see, how do we do? Yeah, it's differentiable on 0 to infinity. Okay, yeah. Because we can't take the log of non-positive numbers. The only critical point is, well, yeah, all right. Okay, so we do have to scrap the 0 because we can't take the log of 0. Let me see. So we have to scrap this one. I'm gonna leave that error there because we didn't identify the domain, right? We can't take the log of 0, so x can't be 0. Okay. So again, note that x equal to 0 is not in the domain, so it's not a critical point. Therefore, the only critical point is the e to the negative 1/2. Okay, that's fine. So, okay, let's look at this. So let's see, right here. It says that theorem 4.1 guarantees the existence of an absolute extrema of a continuous function on a closed interval AB, but it doesn't say where these values are located. Two observations lead to a procedure for locating the absolute extrema values. An absolute extreme value in the interior of an absolute is also called a local extreme value, and we know that the local extreme value occurs at the critical points of f. Absolute extreme values may also occur at the endpoints of the interval of interest. These two facts suggest the following procedure for locating the absolute extreme values of a continuous function on a closed interval. Assume f is continuous on the closed interval AB. Locate the critical points on the open interval AB where the derivative is 0 or does not exist. These points are candidates for absolute, max, and extreme. Evaluate f at all the critical points and the endpoints, and then choose the largest and smallest values from step 2 for the absolute, max, and min values, respectively. So in this example, we're asked to find the absolute, max, and min values of the following functions. Okay, let's get this a go. We should be able to do this. Let's go paper like this. Okay. So for example 4a, we have what? F of x equals x to the 4 minus 2x cubed. Find the extrema on the interval negative 2 to 2. Okay. So let's start by finding the critical points on this open interval. So let's consider f prime of x. We're going to set it equal to 0. F prime is going to be, in this case, 4x cubed minus 6x squared. Okay. We want to set it to 0 and solve. We can factor out a 2x squared from each term. 2x squared. We're left with 2x minus 3 equals 0. All right. So then from here, we get that x equals 0 or x equals 3 by 2. All right. So those would be the candidate. Find the absolute. So these are the critical points. So then we want to evaluate the function when x is 0, when x is 1.5. So then if we consider f of 0, we're going to get the origin. And then if we consider f of 3 by 2, we're going to get 3 by 2 to the power of 4 minus 2 times 3 by 2 cubed. Nine times 9, okay. So then 9 times 9, that's going to be what? 81 over 16 minus 27. What is that? 50. 27 times 2. What is that? 40 plus 14 is 54. So it's going to be 54 over 8. Okay. 81. You can use a calculator. I'm just playing around. Well, top and bottom by 2 is 108 over 16. 91 is going to be negative. 91, 101. So what, 27 by 16? Okay. Oh, it endpoints. So let me see. We have the value of 0 when x is equal to 0. We have a value of negative 27 over 16 when x is 3 by 2. And we need to test the endpoints. So we have a value of something when x is negative 2. So if we plug negative 2 into the original, 2 times 2 is 4 times 4 is 16. Let me see, that's going to be a positive 16 plus 8 times 2 is 16 is going to be 32. And then we have a value of, if we plug in positive 2, it's going to be 16 minus 8 times 2 is 16, which is going to be 0. When x is equal to 2. So then we have a max value of 32 when x is negative 2. That occurs at one endpoint. What kind of max is that? It's an absolute max because it's at an endpoint. Style like this. And then the smallest value is the negative 27. And that's a local minimum and an absolute minimum, right? So we have absolute and local minimum value of this. Let's see, how do we do? Let's put that there. Let's put this here. All right, let's see, how do we do? It just asks us to find the absolute max and min. We didn't have to identify any local. So absolute min, we got an absolute minimum value of negative 27 by 16 at 3 over 2 and a max value of 32. Let's see, how do we do? Now we could look at the graph of this. Oh, the graph is over on the left, right? Let's see. Yeah, it's on the left. We got a max value when x is negative 2 at 32. You see it there on the left. And then a local min. We get the absolute min at 3/2, right, of negative 27 by 16. Those are correct. You can see them in the graph in the upper left-hand corner of the screen. Okay. So I think we got those. Oh, we need to do part B. So let's go ahead and do B. What's the time? 30 minutes? Okay, that's fine. So then part B, we have like that. We have g of x equals, oh, I'm totally out of space. Let me just go like this. X to the 2/3 times 2 minus x on the interval from -1 to 2. So then all of this I want to cut, paste. This needs to go here. This goes next to that. I think I'm missing some stuff. Maybe I just didn't write it. Okay. So we want to find the absolute max and mins. So what we want to do, find a derivative, set it to 0 and solve. Those are going to be critical points that we need to test. We need to test those points and test the endpoints and then take the largest and smallest. Okay. So let's start by considering g prime of x. Looks like my signal is kind of weak. We're going to keep going though. So with the product rule might not be the easiest here. So what I'm going to do is rewrite it. I'm going to distribute this guy. See if that helps. So this is going to be equal to 2x to the 2/3. Let's see. So we add those exponents. So it becomes 5/3, right? X to the 5/3. Okay, let's differentiate that. I feel like that'd just be easier than doing the product rule, because we'd have to do the product rule. The chain rule would be a lot. Okay, so now if we differentiate that manipulation, the exponent comes down. That becomes 4/3 x to the -1/3 minus 5/3 x. 5 minus 3 is what? 2 to the 2/3. Okay. Let's see. We want to set this to 0 and solve, right? I'm going to rewrite this. We got 4/3 over x to the 1/3 minus 5/3 x to the 2/3 over 1 equals 0. So if we get a common denominator of x to the 3rd, we're going to have what? 4/3 minus. That's going to be just an x, right? So we're going to have 5/3 x over x to the 3rd equals 0. So then from here, we would consider let x to the 1/3 equals 0, or this 4/3 minus 5/3 x, we want to set that equal to 0. So from the first one, we get x equals 0. That should make it undefined. What was the original? We're going to let that be, but that's going to be a critical value because it's going to make this thing undefined. And if we solve from here, we add and divide. Add, divide, the 4 is on top, right? So then x equals 4/5. Okay. So we want to test those along with the endpoints. So where's the original? Let me get a copy of this. Copy. Let's paste. Okay. So let's see. Let's start off when x is 0. When x is 0, y is 0. Okay, let's do when x is 4 by 5. So then g of 4 by 5 is going to be 4 by 5 to the power of 2/3 times 2 minus 4 by 5. I'm going to use my calculator to generate that number. Okay, so if we say 4 by 5 to the power of 2/3, let me show what I'm doing, times 2 minus 4 by 5, we'll get this guy. So this is approximately, let's say 41, 1.0341, all right? We need to check the endpoints as well when x is -1. So that's going to be a 1. That's going to be 3. I think the answer should just be 3. Let me do like this. -1 to the power of 2 by 3 times 2 minus a -1, 3. Okay. And then the other endpoint that we need to test is when x is 2. Okay. When x is 2, then g of 2, we're going to have 2 to the 2/3 times 2 minus 2, which is 0. Okay, so the largest y value we got was 3. The smallest y value was 0. So we have, we see an absolute max value of what, 3 at x equals -1. And then we have the absolute minimum value of 0 at x equals 0 and 2. Okay, this is the results that we got. We can actually look at the graph. Like this style, like this. Let's put this back. Okay, max value of 3, and we got the minimum occurred twice when x was 0 and 2. So we see on the far left here a max value of 3 when x is -1. Okay, and the absolute minimum was 0. It occurred twice at 0 and 2. Yeah, we got those. Okay, so that was an adventure. Okay, you just have to do the best you can. I think we have one more. Okay, we have one more. All right. So in this example, it says trajectory high point. A stone is launched vertically upward from a bridge 80 feet above the ground at a speed of 64 feet per second. Its height above ground t seconds after the launch is given by this for the closed interval from 0 to 5. When does the stone reach the maximum height? So we have this function. If we want the maximum value, we want to set the derivative to 0 and consider all the critical values, all the critical points, and the all the necessary points that we need to consider. Okay, so again we have f of t equals, we got this -16t squared plus 64t plus 80, and we're going to consider this on the interval where 0 is less than and t is less than or equal to 5. Okay, so if we consider f prime of t, take the derivative. 16 times 2 is negative 32t plus 64, right? We want to set this to 0. If we set it to 0 and solve, subtract and divide, t equals 64 divided by 32, just 2. So that's a critical number, and we want to also test our endpoints. So when t is 2, we want to consider f of 2 is going to be, oh, we got to plug that in, right? Negative 16 times 2 squared plus 64 times 2 plus 80. Let's see, 32, 64. So it's going to be a negative 64 plus 108 plus 80. That's going to be 64 plus 80 is 144. What is that? That's going to be 144 feet. Okay. We also want to consider the endpoints. So when t is 0, f of 0 is going to give us 16 times 0 squared, 64 times 0 plus 80, which is just 80. Okay. And then we also want to consider t equals to 5, the other endpoint. That's going to be f of 5. Negative 16 times 5 squared plus 64 times 5 plus 80. If you had 16 quarters, it's like $4. It's going to be a negative 400 plus 6 times 5 is 300, so that's 320 plus 80. That's going to be 0, right? So then we have an absolute max value of the highest y value is this 144 feet when x is equal to 2, what is that, seconds? 2 seconds. And then the minimum, let's see, we have an absolute minimum value of 0 feet at x equals 5 seconds. And these are the results that we got. Okay, let's see, how do we do? So it occurs, we said absolute maximum occurs at t equal to, oh, I put x, let's change this to t. T equals 2, at which the stone reached a height of 144 feet. Oh, I guess the question just said find the max, right? The maximum height, yeah, after 2 seconds. Yeah, we didn't need to find the minimum. But there's an application that's basically telling you that it's on the ground, right? For the second part. Okay. All right. Well, that was fun. So hopefully that wasn't too bad. I'll do my best to make sure that assignments are posted, corresponding assignments are posted on Pearson, okay? And I am available for questions. So, make use of the Ask My Instructor. If you don't ask any questions, I can't answer questions that aren't being asked, Make use of the Ask My Instructor. Make use of the tutors. We have tutors. You have support. You have a lot of people here that's eager to help, okay? And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.